Okay. Well, this presentation is just like a brief introduction to quantum computing. I go over some of the big concepts that are in quantum computing, and then I take a look at Shor's algorithm. Feel free to jump in at any point with any comments, questions, or anything. I think that a good place to start, even though I think most everyone already knows this, is the representation of data. It works on quantum bits that are called qubits. These qubits can either be in state 0, in state 1, or in any other state that is a linear combination of these two states. And this comes from Schrodinger's equation, stating that quantum systems evolve according to linear equations. Qubits can be partially measured with a given probability. They are changed by measurement, and they cannot be copied or erased. And at the bottom, it's kind of small, but these are some of the ways that different qubits are implemented. So through superconducting loops, through trapped ions, through silicon quantum dots, topological qubits, stuff like that. So how do we initialize the qubits, actually? This is the example with superconducting qubits. Is that they're kept at extremely low temperatures, and they're designed such that their lowest energy state corresponds to the 0 quantum state. To ensure that the qubit is in the 0 quantum state, microwave pulses can be applied that flip the qubits that are in the 1 state to the 0 state. Then we have the concept of superposition. The definition of it is that the creation of a quantum state where a qubit exists in multiple bits simultaneously, or is a linear combination of multiple bits. Here, this symbol is the state, quantum state. And alpha and beta are complex numbers that specify the probability of measuring the qubits in the states 0 and 1. And alpha squared plus beta squared is going to always equal 1. And at the bottom left, you see this block sphere, I think, is how it's pronounced, where the north pole of it represents state 0, the south pole of it represents state 1, and any point on the sphere is a representation of a superposition state. And the bottom right, we see Schrodinger's cat, of course, the cat that is dead or alive, or some combination of both within the box. Here's a bigger.
Anyone who is an engineer and studied Fourier transform can easily understand superposition. Take 2 sine waves, combine them, and you get a new signal. This is superposition. Any signal is a linear combination of can be represented as a linear combination of waves of fixed frequency. That's superposition. And because of that, as a side effect, Heisenberg uncertainty principle. It's that Fourier, the short window Fourier transform. You cannot know frequency content instantaneously because there is not enough low frequencies. If you push your window too narrow and so on. So you have to, if you want low frequencies, then you have to have a large space uncertainty or time uncertainty signal efficiency. Then only then you capture low frequencies. And it's same thing here.
Here's another.
Yeah, like superposition and it's just a linear combination, weighted linear combination.
Of the 2 states. Another Schrodinger's cat, the excellence of it.
Well, and Schrodinger came up with this example to tell people how stupid they are, not how we interpret this example.
Yeah, but it's fun.
He said it's just like it's nonsense to think about it this way, and everyone is like, "Oh, it's so esoteric. Cat is either dead or alive, or both."
I just like that there's cats. The rest.
Oh yes, cats sell.
Yeah.
Absolutely. They were selling cats were selling well before YouTube. There's even a movie about an artist in Great Britain, played by whatever, I forgot the guy's name, Doctor Strange, actor.
Benedict Cumberbatch.
Yeah, Cumberbatch. About this guy's going. Oh, well, it's a movie for our crowd because he goes schizophrenia, like he develops disorder, and then he draws those crazier and crazier pictures, cats. Yes, I highly recommend that movie.
Check it out.
I forgot what it's called though.
Imitation game?
No.
No.
Then
That's about Alan Turing, that name I remember. But that article, I don't remember, yeah.
Then we have entanglement. An entanglement is the phenomenon where the states of two or more qubits become linked regardless of the distance or their physical separation. So a state of one qubit directly depends on the state of the other. So for example, if the state of one changes, the other is instantly adjusted as well. Or if a measurement is made on one, the other will automatically collapse. And here we have
That's an incorrect phrasing, sorry. Nothing instantly is adjusted, it's that we can tell, it's a tricky phrasing. It's sort of, if we measure, the thing about quantum anything is that by measurement, you destroy the object. You have to absorb it in an atom in order to say, okay, I measured the photon, right? So you destroyed one, but then, for example, polarization, you have to put a polarizer filter, and if a photon goes through the polarizer instead of being blocked by it, then you know something about the other one. If they're negatively correlated, it will not go through the polarizer. If they're positively correlated, it will say, oh, it is it will go through polarizer. But nothing it's not that you can adjust thing here and it adjusts there. No.
So are you actually destroying a physical object, or are you destroying like a conceptual object? I'm kind of thinking, what's coming to mind is like the money hole problem, where you like, if you learn about the door, you need to switch your choice, no matter what choice you're.
No, you're destroying the physical object.
Okay.
Quantum. You're absorbing the energy. In order to recognize that there was a photon, you have to absorb it, and you cannot let it through.
Okay.
Your atom changed your the excitation level by absorbing that in the detector. So, and that's it. So this photon, so you can only hope for the group property that other photon, like imagine there is a source and some effect that you want to get, and there is a detection here. If you detect everything from the source, nothing gets here and the experiment doesn't happen, but you know what is coming. If you just like that, like you cannot catch the photon, talk to it, look at it, and say, oh, good, here, go. You cannot do that. It's like, that's it, it's gone. If you measure it. If you don't measure it, it keeps going somewhere until somebody else measures it. And somebody else is this table, the owl piece of this book. It's not an observer. This is everything, every atom is an observer in this case, by absorbing the energy.
So you have an issue here with the word instantly?
Instantly adjusted. Nothing is adjusted, it is already.
So like
it's a super correlation. You super correlate two photons.
Well, here, I have a question, because I'm gonna get to the gates in a second, and they have a gate that if it's 0, it instantly flips it to 1. So why isn't this the case over here?
But the photon doesn't go through. It flips it, yeah.
what photon? So what I've heard, so I'm not, knowledge in this, but
Yeah.
I've heard that if two qubits are entangled, one in New York, the other one in San Francisco, if you measure the other one, the other one instantly messed up, or like their entanglement is messed up. Is that not what you're saying? You're saying
Yes. Yeah, that's not what you're saying.
how-
If you measure the one, you will learn something about the other.
but that's instantly. That's what is interesting about it. It's like faster than the speed of light or whatever.
But you just-
I'm not sure. I never hear 100% explanation. This is something like you wake up in the morning, and we know about you that you always put different colors of socks on, and you have 2 colors only. And then I see a blue sock on your leg, and I instantly know what is on your other leg, kind of thing, because they're super correlated. The thing with quantum is there is so much noise that it's surprising that so far away it will still preserve that property that they were in the beginning. It's not that anything is instantly changing.
So no, that's exactly what I've heard, that the problem is not the distance, the problem is the instantaneousness of it. That is like faster than anything that can happen in the universe.
No, but I don't think anything happens.
You just
Yeah,
learn-
exactly.
You just learn information. If they're entangled, then they share a piece of information. If you observe either one, you instantaneously learn information about the other guy. But
It's destroyed.
they stop being entangled afterwards. So
Well, the other one is destroyed.
yeah. So it's not that you're transmitting any information at all. There's still one coherent system that you can say one thing about the other guy by observing this guy.
Yeah, it's not that you're changing this and the other one tunes. No,
You're
no,
missing
you're learning
the-
about the
okay.
other.
Whatever one the first one is, the next one will be it.
Like the socks example. If you know the left, if William says wear the same socks more consistently than suggest, then you know like, okay, one sock is black, the other one is black. Even though you don't see it. Something more like that, you're learning information. And why it is surprising, because systems tend to decohere super quick, that's why we cannot build a reliable quantum computer of any kind of scale, so still, because it's like super hard to keep the system in coherence. That's why Penrose's theory is being criticized. Our brain, to keep anything in coherence at low state in 0 Kelvin, it's like just where, how, it's just so unbelievable. That's
This idea about consciousness that what you're talking about.
I'm arguing about quantum effects powering our brain. Well, I mean, they do, because our brains are made of atoms and particles and stuff, but not in the sense of quantum computers. Yeah, it's fun to talk about things we don't understand, consciousness, quantum computers and stuff.
He had a
But,
very good podcast on Joe Rogan if you're interested. Roger Penrose. And he explained that whole thing for 3 hours. I didn't really understand it, but it was interesting.
Roger Penrose?
Yeah.
I didn't know, okay,
It's
good.
very old, like
Yeah, you need
Oh, no.
quantum microtubules because consciousness is incomputable, because gravity, because whatever.
that's
Yeah, I did watch that podcast. It was
You did?
hilarious.
And we have interference, the definition of which is that quantum states can combine in ways that amplify or cancel the probabilities of outcomes. This is like constructive and destructive interference in physics that we learn. For
Yeah,
example,
those are just wave
Yeah.
superposition,
Yeah.
right? It's
Simple.
just very simple.
yeah.
It's complicated in physics because it's real world.
Yeah.
But concept we learn,
Yeah.
early in our education.
One of the example is applying a Hadamard, I don't know.
Adamard, he's a French, H is silent, but
I
okay.
don't know.
Americans, what do they know?
Well, we call it an H. To a qubit twice. This has no classical equivalent from what I can tell. So this is the matrix that represents the H gate. And if you apply it to a state 0, this is the output that you get, because 0 is matrix 1 and then 0. And then if you apply it to state 1, you get this. So if you apply the H gate to a qubit of state 0 twice, you get the qubit itself unchanged, or reverses the change on itself. So regarding the necessity of the 3 previous concepts, phenomena, while all 3 aren't necessary for every single computation, the algorithms and calculations that provide a quantum advantage do use all 3 simultaneously. Other examples down there of ones that, for example, use superposition alone, which is useful in quantum random number generators, parallelism for evaluation of functions, entanglement alone used for quantum teleportation, interference alone essential for quantum sensing, but all 3 are needed for example, Shor's and Grover's algorithms and most quantum machine learning algorithms.
What are needed? Entanglement is needed?
Yes. So it's not needed for every single quantum operation, but for the operations that seem to be performing better than classical algorithms, all 3 are needed.
Okay, so even for Grover and Shor, you
Yes.
need 2.
You need all 3.
Yeah, well, I can get by with 1 and 3 without quantum, but
But yes.
okay. But back to the just a little bit of the previous slide, the gates or transformations and absorbing the light. Right, there's this Huygens model of waves that we also learn when we learn about wave physics in school or whatever, undergrads. Huygens, Fresnel, have you heard of those? Fresnel, I don't know, it's probably pronounced Fresnel in, yeah, but again, French guys. So the model is that there is not a single wave propagation. It's like each point is emitting a spherical wave, and then the next point picks it up and emits a spherical wave. So like the light particle goes in and it excites, and the next particle emits, then absorbs, excites, and it's kind of like a chain reaction thing. So you can think about it that way. I'm just thinking about this transport and sleight of hand, the magician. We started talking about physics, and then quickly, without an explanation, we're in linear algebra. Physics disappeared. We have no idea how all this can work or works, and we start manipulating linear algebra, which we are comfortable with, and we build a castle in the sky on that. That if, then yeah, if that was true, then that's true. But like, I have a problem with this guy.
From the definition.
What is
yeah.
happening there from going, but the rest I'm fine with, and the stuff before I'm sort of fine with. Like, okay, sorry.
So data retrieval and manipulation, we already kind of went over this. So a register, which is a collection of qubits, can exist in a superposition of many different states. For example, an n-qubit register can represent all 2 to the power of n possible combinations of zeros and ones at the same time. But when you measure data from a quantum register, the superposition collapses to a single classical state. So why does this happen? Because of quantum decoherence, which I already mentioned, which is the loss of superposition due to a spontaneous interaction between a quantum system and its environment. So this is an example, it's a very simple one, of how the probabilities are used to measure which state it's going to be in. So the probability of reading the rightmost bit as 0 will be this squared plus this squared equals that.
Think about this as a wave, or as a signal, and the square is the power of that signal. So, and think of measurement as a short in the circuit. Like so the more the power, the larger the probability that it will short at this position. That's how you can interpret the square, what is going on, why the probability is the square.
Also, it doesn't like the psi function, psi star, like aren't they like complex conjugates or something like this? Like that you have to actually have like two.
Yeah, it's a wave equation. You have to have phase and amplitude.
Oh, okay.
Yeah, so complex part is the phase. I mean, it's not the phase. Euler representation of the complex number gives you the exact idea of what is the amplitude and what is the phase, right? So you have phase and amplitude, and you can decompose it by Euler's equation into sine and cosine.
A bit about quantum gates and circuits. So like classical logic gates, quantum gates are basic quantum circuits that operate on qubits. Every gate operation U has to be unitary, satisfying U times U transpose is equal to the identity matrix. And quantum gates ensure that probabilities always sum to 1. All quantum gates are reversible, meaning that the input can be conducted from the output. This is, of course, if they have not been measured. Measurement does not apply to these. We have an example of the CNOT gate, the controlled NOT gate, which acts on 2 qubits, a control qubit, which is usually the first qubit, and the second qubit, which is the target qubit. So if the control qubit is set to 0, the target qubit remains the same. If the control qubit is set to 1, the target qubit is flipped. You can see the examples down there. And there is a matrix representation of it. And then we have the Bell state, which is when the qubits and the gates are used to generate an entanglement state. They call it a Bell state. There are, I think, 4 Bell states. This is just a overarching example of one. So you initialize. You start with 2 qubits in the state 0. And the joint state of the system will be 0, 0. You apply an H gate to the first qubit. The H gate transforms the state 0 into the superposition that we see here. And then this will result in a combined state of the H gate that's been applied with the second qubit, which will result in this. And then you apply a C0 gate. And this keeps the first qubit as the control and the second qubit as the target. So the C0 gate flips the state of the target qubit if the control is 1. So it says 0, the second one remains 0, and the state 1, it flips the target, so the 0 becomes 1. And this creates entanglement. A bit about quantum programming. This is some of the quantum programming languages that are used. Examples of them, you have the QCL, the IBM Qiskit. You have Q#, Cirq. There are a whole lot more that are being created, but these are just for the examples that I found examples for.
So what do you mean quantum programming? They work for quantum computers or regular computers as well?
Both. So, for example, the IBM Qiskit, you can code it on your own computer, and then it connects with a cloud to a quantum computer somewhere, and then that's how you code it. Some of them are for the computers. I didn't look too much into this. I don't have a strong answer for you. This is Microsoft's language.
C# is? I mean, the Q#.
yeah.
I thought so.
So this answer, the next slide answers the question that I wanted to ask earlier.
What question?
I wanted you to explain Shor's algorithm.
So Shor's algorithm, this is the problem statement. Given an integer n, find its prime factors p and q such that n is equal to p times q. So classical algorithms that solve this problem usually take super polynomial time. And for example, the trial division algorithm, which checks all integers up to the square root of n. Pollard's row algorithm that uses a pseudo-random sequence to find factors. And the general number field set that factorizes large integers using algebraic number fields take too much time. Shor's quantum algorithm runs in polynomial time. So yeah. There's an overview of Shor's algorithm. Again,
Wait, logarithmic, right?
Logarithmic cubed is.
yeah,
Is logarithmic.
Okay,
I wrote it wrong.
I was curious, is there a way?
Or what is the log n times log n, or what is written there?
I think it's n cubed times log n.
Or log n cubed?
Yeah.
So 3 log n. Log n.
Okay.
Log n. Well, this is the one that was in the paper that I read, so I just put it there.
Yeah, that's confusing, what's written there, yeah. Okay,
It's log n.
well,
Log.
I just checked.
short.
Yeah.
No. Log n
It's a
is,
specific one.
So this is the algorithm that people kind of hype up as potentially breaking RSA, I guess.
Yes.
Yeah.
So this is the overview. So again, we have the problem statement, you have an integer n, find its prime factors p and q such that n is equal to p times q. So the step 1 is you choose a random integer a.
and n is again what, number of digits in the integer?
It's just
or-
any integer. For example, 564.
It's the size of the integer itself.
And log n in the size of the integer. Okay,
Well, the size of the integer also tells you how many numbers you have to check. So, same thing.
okay.
You choose a random integer a such that a is greater than 1 but less than n. There's another variation of this algorithm that says this random integer a should be greater than n and less than n squared. But this is the one that I found. You compute the greatest common divisor of a and n. And if the greatest common divisor, the GCD of a and n is not equal to 1, a non-trivial factor of n is found. Then this is where the quantum step comes in. It's step 3, which we'll go through in a second. You're going to find the order r of a mod n, which will be the smallest positive integer r such that a to the power of r is equal to 1 mod n. And if the order r that you find is even and this condition is met, you compute the factor 1 and you compute factor 2 and you have your two factors. If any of the conditions are not satisfied, you repeat the algorithm by choosing a new random integer a. So, step 3, the quantum step. Quantum period finding here is used to find order R efficiently. And as a reminder, order R is the smallest positive integer R such that a to the power of R is equal to 1 mod n. So the first thing you want to do is to construct a quantum state that represents a superposition of all possible exponents. Quantum computers use 2 registers for this. The first register is initialized from 0 to 2 to the power of n minus 1, where n is the number of qubits. And the second register is initialized to 0. This is the mathematical representation of that. This term here, 1 over root of 2 to the power of n, normalizes the superposition, so the total probability is equal to 1. The summation sums over all possible values of x that the first register can take, and the second register is initialized to 0. Then you apply the modular exponentiation function. F of x is equal to a to the power of x mod n to the second register. And this is where the entanglement comes in. So this operation entangles the state of the first register with the results of the second register. As you can see in the equation, the only thing that's changed is that the second state has been replaced by the modular exponentiation function. We measure the second register. So we measure the second register, assume that it gives us value k, and then the first register collapses to a superposition of all x such that a to the power of x mod n is equal to k. So we can denote this set of x values as x naught plus r, x naught plus 2r. And this state after is a superposition of all the x values that satisfy the condition we had in the previous step with the modular exponentiation function. Here you see the mathematical representation of what happens after that, where j is just an integer multiple of r, order r. K is the value that we find after the measurement of the second register, and m is approximated to 2 to the power of n over r. Then we apply the quantum Fourier transform, which is the quantum analog of the discrete Fourier transform. It performs a linear transformation on qubits and is used for tasks such as period finding and phase estimation. What the QFT does is that it maps the state x to a new state y, and this is the equation for it. And this whole lot of exponents, this complex exponential term, is what encodes the phase information of the original state and the new state. So we're going to apply this to our superposition. And this is the resulting equation that we get. And this simplifies to this one right here. There were a lot of steps. So what does applying the QFT actually do? The initial state before the QFT is a superposition of states that periodically repeats with period r. Order r is the one we're trying to find. So what this is it maps the periodic superposition in the time domain to the frequency domain. And this is where interference comes in. So this operation shifts the basis from the computational basis, where each state represents an integer, to the frequency domain, where each state represents a possible period. And then after applying the QFT, the period manifests itself as frequency peaks at integer multiples of 2 to the power of n over r.
And quantum Fourier transform is constant time or what?
Yes, I think. I didn't check.
Well, it's n log n in the normal world, right? So what are they getting? But in reality, quantum in physics, Fourier transform is constant time passed through a media, through a filter, and everything takes the same time to pass through a filter, and it's Fourier transform. But what is going on there?
I don't know.
Okay. Just too many moving pieces.
Yeah.
Yeah.
I wanted to explain it in detail, but it was a lot.
Well, I mean, I'm not able to keep up.
Neither am I. So you apply the QFT, okay, and after you apply the QFT, you measure the first register. So this collapses the superposition to only one of the states, which is the k times 2n to the power 2 to the power n over r. And the probability of measuring a particular value depends on the amplitudes of the states, which are now evenly spread across the frequencies by the q at t. Then we're likely to measure a value close to m times 2 to the power of n over r for some integer m. And following this measurement, the state collapses to y. Then you just do classical post-processing. You suppose that the measured value that we got here from the collapse state is y. You said y equal to m times 2 to the power of n over r, which we got from this right here. And you calculate the ratio, and then using the continued fractions algorithm, you approximate m over r, which helps you identify the denominator r, which gives you the order r, which is equal to a mod n.
So quantum, at least according to Wikipedia, quantum Fourier transform is n log n. So I wonder,
Is that the size of the number? The size of the state?
the number of qubits. It requires only n log n gates to achieve efficient approximation.
Claude is telling me that it's O n squared, where n is the number of qubits. So it should be.
Well, but there is an efficient approximation in n log n.
But is n the size of the?
And
number of
qubits is the size of your number that you can process. If you're using an n log n algorithm, how can you check?
Well, the n over here is not the number of qubits, the n over here is the size of your number.
Yeah, but how do you
Factor.
store a larger number? You need the n qubits for,
No, you need log two,
Yeah, exactly.
log two and.
Yeah, you need log n
qubits.
bits to store a number
So
and
with
Mhm.
like
Yeah.
3 qubits, you can. 256 numbers.
yeah, so if it's n squared, then the time complexity will be log n squared, so it's 2 log n. To apply q of quantum q of t to a number of size n.
Okay.
I think I'm doing the math right.
I did wrong here, but yeah.
So what's the max number of qubits we can, or that are in existing quantum computers?
I heard 16, but maybe I don't. That's a lot. I think D wave is 2, but there are many of them, but they're not entangled.
Error correction, you mentioned quantum decoherence earlier, but quantum states are very highly susceptible to errors. So error correction techniques are necessary to detect and correct these errors without actually measuring the quantum state, because that causes it to collapse. So there are these quantum error correction codes. Shor himself has a code which encodes 1 qubit into 9 qubits. Steen's code encodes 1 qubit into 7 qubits, and then surface codes, which are a new thing, I guess, use a 2D grid of qubits. So these encodings spread the information of the qubit across multiple physical qubits. A series of parity checks are performed on these additional qubits, and then they're measured. So the measurement of the additional qubits can help infer what the issue with the actual qubit is without needing to measure it. This is one of the techniques that they use to help get information about the type and location of errors. Applications, this is the RSA thing. Quantum factoring can be done exponentially faster than on classical computers. This little table I found on a presentation somewhere, so I have no idea how accurate it is. But it shows maybe it overemphasizes or exaggerates how, if they work, quantum computers can revolutionize this factoring thing. And the big concern will be then that the public key cryptography, or RSA, relies on the inability to factor such large numbers, so we can do them in less than 1 second. That causes a big concern for our security. That's it.
Done?
Do quantum Twingo.
As in what?
Clinker, that's what I use. Programming.
Well, but as Pavel was talking about in his talks, it's very hard to quickly input information and read information from those devices. It's like, it's almost like you have a mechanical system where you crank a thing and then it's quickly computed and then you crank it when you get. And then by this time, the classical computer has already finished its times because of. Okay, yeah, I liked your slides and presentation and all of this little crayfish crawling around and scaring the little boys. But yeah, I wasn't able to frankly follow how this algorithm works and how does it have anything to do with what I can understand. So I don't know, I hope you understand Shor algorithms now perfectly and you can go home and in your garage build this. You can factor 15 on quantum computing.
Yeah.
So what do you think about Microsoft Simulator Q#? Does it help? Is it interesting at all? This, yeah, or SERP or whatever.
Sir, these are the original ones, I guess. I haven't looked into them enough to see. They look simple, too simple for quantum computing in my mind.
The front end looks simple.
Yeah, different.
Well, and on one hand, it's supposed to be, but on the other hand, this is like other libraries and Babbage, like they're writing things for things that don't exist.
Yeah.
Right? So your language could be anything, pretty much, right?
But once it does, like Babbage, we're gonna be like probably talking about them a little bit. Or if it does, I should say, but
No. Can you repeat the statement? Once it does.
or once we actually can apply it though, we'll be talking about these whoever creates the language in the same way that we're talking about Babbage now.
Yeah, with a funny intonation and exactly. I mean, nobody used any of the stuff that Lovelace and Babbage created, and nobody knew about it. They came up with their own languages that were ugly assembly languages of the machines that they were building. They were never close to anything, the castle in the sky, and then they came up with Fortran. And yeah, kind of went back to high level languages only way later. Like there is a thing called evolution, and it's kind of objective, right? We observe it in everything. And evolution happens in technical systems as well. And we have around 200 years of observation on technical system evolution. So we can predict at least trends of how previous inventions develop. And like this maps to me to Babbage. If the guy, I think, it takes different kinds of people to do things. So Babbage never actually done anything, unfortunately. And even when they reproduced his work by his blueprints in the 20th century, it didn't work. They had to fix the design in order to make it work. So he never built it. He was just dreaming about it, which is needed, but you know, he needed Steve Jobs or somebody, the guy who like doesn't care about or doesn't know how to make things, but wants to sell them and to make them work. So like here, I think we can find parallels in it, and it's computing is just one parallel. It's just too close to us, but there are any technical system goes through stages of evolution. So I wonder how this the quantum computing would go. Anything else actually also had faster return than quantum computing. Quantum computing is funded since the 90s. So 30 years now.
This algorithm came out in 1994.
Thank you for supporting my statement.
Yes. I was just
That David Deutsch talked about that in the 80s or something, or 70s, and yeah. So I wonder, on one hand, our civilization of TikTokers lost the ability of long focus, and building pyramids is not our thing. We will get bored in 3 generations. Oh no, we will get bored tomorrow, sorry. But yeah, but on the other hand, like how long can we wait, or shall we wait, or like, I mean, we as society who invests in the new things, right? I'm fine with IBM investing it, right? It's their money.
Yeah, I mean, if it's a dead end, man, a ton of money have gone into it, that's,
But we don't know without trying.
yeah, I know. And that kind of is what, like you're going back full circle, people say about string theory.
Yeah, I was gonna say physics is kind of in a similar boat.
But without going into dead ends, how can we? Well,
Yeah.
how can we reach? We never. What is it? Prediction is difficult, especially about the future. So we don't know. If we knew what we're doing, it wouldn't be called research, right? So we don't know, and we need to explore. But where is that limit? And maybe there. Another hope is that you, as starting scientist, will look at it and will have a feeling I can do better. It's like, hey, I don't need this quantum entanglement. I can implement those algorithms on a RC circuit or something like, just
Quantum gravity computer. That's, yeah.
Quantum gravity, which is real, by the way.
at least it's real. Right? No, I mean, this is real too, but there are differences between real and technically feasible.
I mean, yeah, same thing for Shor's algorithm. It scales log and with the size of the integer, but your quantum computers get worse exponentially with the number of qubits. So
That sounds like the law of either Nicholas Weird or Dijkstra, is that software slows down exponentially faster than hardware speeds up. It's an anti-Moore's law.
yeah, it's an inversion of Moore's law, I guess. Yeah.
Well, I mean, it's compensation.
Mhm.
You get exponential increase in productivity,
Yeah.
but your programmers
Mhm.
get worse and worse.
Yeah, the physicists are weird. I hang out with the physics department over at Tech quite a bit, and they don't believe in themselves for the most part. They all still live in the 1930s. They still think that generation was the best generation of physicists, and no one afterwards has kind of lived up to them.
That's weird.
Even lecturers kind of say that about themselves and about their whole generation, and also about the students. And so it's like, if you don't believe in the ability of future physicists to do anything about the field, then why bother?
But that's weird because right before quantum, well, Planck was doing it already. While Planck was inventing quantum physics, Max Planck. I forgot, somebody said that all the problems are solved, and only there are like little clouds on the horizon that don't matter, and all the problems are solved completely. And then
Why are you pessimistic about the quantum computers? That first of all, it's already been done in just a few bits, but it's like the problem to scale. And I think with AI coming, everything can be solved with more energy.
the more energy is kind
Yeah,
of.
I've heard that, but some companies like Google are building a nuclear power station right next to their data centers just to compensate their.
Yeah, it's Amazon.
That was Amazon, yeah.
Are they really?
Yeah.
What are they gonna do with the runoff then? Because we still have.
Well, the thing is, Amazon makes like 80% of their profits through AWS anyway, so it makes a lot of sense that they're doing that.
And you make
Yeah.
your own electricity and you put that peak of an AI on top of this, it's gonna solve it.
No, I think the problem with quantum computing is a bit more intractable in that it's the quantum error correction not being, well, no one has a decent algorithm so far. And even though you can build a quantum computer with more qubits, and you can slap more on, but the error rate of your computer grows exponentially with a number of bits. So now we have 16, but the problem becomes twice as hard if you have 17. twice harder than that at 18 and so on. So it doesn't really work, yeah.
Well, it's not impossible, if anything, it's not impossible.
Yeah, we have a mathematical proof that such an algorithm exists from like the 90s. It's like the quantum version
I
of
would
Shannon's
bet
thing.
on it in the long term.
I mean, sure, yeah, but maybe the AI people figure out how to make God before then, and then we don't have to solve that problem anymore.
I'm just very excited for, it sounds like a lot of potential energy, it's just gonna snap at some point, and all of a sudden everything's gonna fall in line. With how it's coming across, cause I mean, if we, and it sounds like a hindsight bias, really, cause if we think about, in the '80s, I mean, I just think about the '90s, we thought that what computers were gonna be running a lot of things, right? But then now we aren't really thinking about that, we're thinking about AI, and I just kind of see the perception changing in a decade. Perhaps something will, something new and innovative will come across that will make us think about something different. I almost think about it as in the '80s, we thought oil was gonna run out, I think, around the time 2000s, I think. But then people figured out how to use fracking technology, and hydraulic fracturing then was able to get more out of that curve. And that was more an innovative approach to a problem, as opposed to just that kind of changed up a linear prediction, but yeah, sorry. So maybe,
No, no, right.
so maybe that'll change, maybe there'll be something more creative that'll come across.
Within quantum computing or in parallel outside?
Probably both, it could be with cause it, like I think Mike was saying the error rate's just kind of there, and that seems like the ubiquitous problem across well, physics too, because it really comes down to the fact that by the nature of quantum mechanics itself, and we just don't have an approach to that really. So I mean, once that kind of becomes more uniformed in both those fields, it just kind of seems like which really just sounds like it just needs a better approach to a math, or a better math, or a creative problem, creative solution, sorry, as opposed to the problem, which I mean could just happen at some point. There's not really a way to predict where it's going or progressing.
I mean, yeah. We're all outsiders of the field, so we can't really make a prediction on it, but
Yeah.
from all of the blogs that I read on, from people like Scott Aronson, it doesn't seem like they have an actual clue how to make these quantum error correction codes. So it's not like in mathematics, like the Millennium problems where we have pieces of a solution kind of laying about all over the place. We have no clue how to do any of this. And no one really, yeah, it's like, it's impossible to make an inference at all. There's no line for you to make a linear prediction off of.
It's just astounding to think about how big a hype train can get if it doesn't work out, like.
Do we actually know how much money, because I brought that up earlier, like how much money was dumped on that? I'm just kind of really curious now, like how, do you know how much money was invested in quantum computing? Because that would be really disappointing. 1994, you said, was
when the algorithm came out, assuming in the billions.
Imagine like an AI that runs on a small quantum.
Don't worry, the more billions were burned in the wars that didn't lead to anything. To actually negative result. So I mean, I'm not worried about billions because they created more students in the field, even those who are disappointed by quantum, but they came from quantum and they went to a different field. They were fed by this money, and so that's kind of, it's not just the money, but it's more about looking for the non-obscene word, but kind of like intellectual idleness, or like you're solving problems that don't matter, like kind of.
But quantum is very important, and all the chips in your phone, the transistors work with the quantum physics.
Of course,
Yeah, so
has
the-
nothing to do with quantum computing, yeah.
But
with Farnsworth, I think it was Farnsworth, you said, sorry for.
the transistors,
Okay.
the transistors in any chip that you work with, they have to be at the level of quantum.
No,
It's not-
quantum effects, quantum physics, yes, but don't mix one with another.
We try to
Doesn't say anything about quantum computing. Our world
Okay.
depends on quantum physics heavily. Turn off quantum physics and we'll lose all of your TikToks. That's it, immediately, like everything TikTok connected, like
So
all of
I
the
think
computing. People don't realize
even-
that, yeah.
Even if computer, even if quantum computing is a giant, like, waste
Has
of
nothing
money,
to do, yeah, it's not.
even if it's a giant waste of money, it's so small compared to the whole field, like, it
No, but the
makes
whole field is not a waste.
Yeah, that's
That's
what I
what,
mean.
like, the question is about waste versus not waste.
No, I
No,
mean,
there's actually, I mean, even if the quantum computing doesn't pan out,
it's a
the,
side project.
the, all of the information that's gone into building it has built a lot of other fields that would probably.
Yeah, that are working, yeah.
Yeah.
Well, not exactly. We are not, we're feeding quantum computing. We're not getting anything from it yet. Like, I don't agree as it, like, your formulation was like, as if it's feeding the rest. No, it's not. It's just a side project
Okay,
for the entire field.
yeah.
But why not? We need more, okay, let's think about the other way. Let me formulate it sharply. So a large attractor attracts more brains. So there is a brain drain into a hole of quantum computing that is probably non-recoverable. So instead, why don't we do a startup incubator? Let's try different non-quantum computing, para-quantum computing, under quantum computing. Like instead of exploring, we created an attractor that sucks the brains because it's so cool and spooky, and people are trying, like, creating the mythology around it, putting no, that's a different story. Whatever the destroyer statue in the CERN, like all of that. That's fun stuff. But what I'm saying is, what if it's just a brain drain? In literally, like, yeah, lots of people spending time thinking about a problem that doesn't have a solution. Could be the opposite. Could be, yes, good, we're not spending enough time, like with AI. Well, we haven't done much anyways, but yeah, lots of people started to think about deep learning, and then we seem to have results. At least we've tried to scale it with ChatGPT, and that got everyone excited. But the question is, parallel search or focused effort on one? A focused effort sometimes pans out, right? Like rockets. But there was a weapon there, application propelled the space exploration. So it was fear-mongering again. That's what those AI hipsters want to give us the money, like for Manhattan Project.
I mean, they're working with Los Alamos now, so.
Here we go.
Yeah, OpenAI is working with Los Alamos for bioengineering.
Okay, that was interesting discussions. Thank you everyone who has joined, and thank you Armina for nice slides. I really enjoyed the memes and everything, the handcrafted stuff. Yeah, next time we will be grammatically correct, and we will hear a story about a research all about research into octopuses. Those creatures with multiple brains, and they supposedly don't know what their left hand is doing with their right hand because their hands are the brains. Yeah, so I don't know. Let's figure out. Come join us next week. Thanks.